In this session, we're going to look at some of the bitwise operators that are available to you in the C language. There are two main reasons we'd use bitwise operators. The first are logical operators, where we can work with individual bits, and the second would be to do binary arithmetic. And we'll take a look at that in a second. So we're going to start with logical operations. And we can see the operators here. So we have a tilde, we have an ampersand, we have a pipe, and we have a caret. So let's take a look at the tilde first. So the tilde is an inversion operator. And so what it's going to do is it's going to perform a ones complement, or an inversion, of each individual bit in the byte. So say, for example, we have the hexadecimal value 7a. So that would be 0, 1, 1, 1, 1, 0, 1, 0. And we have that written here. So we have 7a. So what's going to happen is each bit is going to get inverted. So our result is going to be 1, 0, 0, 0 for the first nibble, 0, 1, 0, 1 for the second nibble. So each bit on its own is inverted. Now if we look at our AND operator, so this is our ampersand. So this expression says we're going to take what's in value, do a bitwise AND with the value hexadecimal 37, and store it back into value. So here we have value, which is 7a. Here we have hexadecimal 37. And what's going to happen is we're going to look at each bit individually. So we're going to start at the right-hand side, and we're going to say 0 and 1. Well, we know with an AND operator that it's only going to be true if both of them are a 1. So this is going to be a 0. Next set of bits is a 1 and a 1. Here, we're going to get a 1. Next pair is a 0 and a 1. So we're going to get a 0. Next pair, a 1 and a 0. So again, we're going to get a 0. The next two, we have 1s for both, so we're going to get 2 1s. Next set, we have a 0 and a 1, and a 0 and a 0, so both of those are going to be 0. So what we have done here is check to see which of the bits here in our original value, of the ones we specified, so these 3 or these 2, so which ones are set. So we've used this as a testing purpose here. Now if we take a look at the OR operators, and this is where we're going to use the pipe symbol. So here we're going to take value, which is 7a. We're going to take 37 in hex, which is the value specified here, and we're going to OR them together. And again, it's bit by bit. So an OR operator, as long as one of them is a high, the output will be high. So here we have a 1. Here we're going to get a 1, a 1, and a 1, 1, a 1, a 1, and it's only this most significant bit where we don't have a 1 in either values. So our output here is going to be 0, 1, 1, 1, 1, 1, 1, 1. Now finally the exclusive OR. So we use the caret symbol for that. So we're going to take value, which is 7a. We're going to exclusive OR it with 37. And exclusive OR, remember, is going to output a high when they're different. So let's look for pairs that are different. So the first, least significant, they're different. They're the same, they're different, they're different. They're the same, they're different, they're the same. So we're going to end up with 0, the most significant are the same, they're different, they're the same, they're the same, they're different, they're different, they're the same, they're different. So why would we ever want to do these things? Well, there are a couple of very common things. So the first thing that we often want to do is to block off or mask something from view, or to clear it. So we have a particular bit we want to output, we want to turn an LED off, for example. Then what we can do is AND that particular bit with a 0. So if we have a starting value of FF and we AND it with 08, what are we going to get? Well, we're going to get all the bits turned off when our mask is 0, and we're going to leave that bit on. So here, a 1 to leave it alone, or to see if it's set. So we've masked off the ones with the zeros, and we've left alone the ones with a 1. Now, if we can also use an inverted input. So if we want to AND something with not 0, it will leave it alone, or we can AND it with not 1, and that will turn it off. Now, we can also OR things, and if we OR something with 0, it's going to leave it alone. So let's take a look at an input value of 111, and let's do half and half this time. So if we OR something with we'll OR it with CC. So the bits that are ORed with 0 stay the same. So if we're doing an OR here, so these two, when we ORed it with 0, stayed the same. And the ones that were ORed with a 1, we made sure they were turned on. Finally, why would we use an exclusive OR? If we want it left alone, we're going to exclusive OR it with a 0. But if we want to toggle it, and this is the key word here, to toggle. So with an AND, we could set or clear, but if we want to change it, we would use an exclusive OR. So far, the bitwise operators we've looked at have all had to do with logical operations, but we also have binary arithmetic ones as well. And those two are the left shift and the right shift. So say, for example, we had the value 4. And we know in binary that would be represented by 0000, 0100. Now if we do a left shift, so we can see the operator here is a left pointing arrow, we can shift it n positions. So let's choose 1 for now. We're going to shift it 1 position. So if we take all of these digits here and we shift them 1 position to the left, we're going to have 0, 0, 0, 0, 0, 1, 0, 0, and then we have a space at the end. And what we do is we fill that space with a 0. So now we can see that our output is 0, 0, 8. So we started with 4, and now we have 8. So we've multiplied by 2 by shifting 1 position to the left. If we take that 8 and we shift to the right this time, so we have a right pointing arrow, we're going to shift 1 position. So we're going to do the same thing. Shift each bit over 1 spot. We have a space at the end, which we're going to fill with a 0. And what do we have here? We have 0, 4. So we started with 8, we shifted to the right, and we got 4. What happens to this guy out here? It gets discarded. So if we were to shift 2 times to the right, so let's start with our 4, and we'll go 2 times. So we're going to lose this one, and we're going to fill in the space here with a 0. We have 2, we shift 1 more time, scale with a 0, we can see that we took that 4, we shifted it twice, and we now have 1. So we can multiply by 2 to the n, or we can divide by 2 to the n using the left shift and the right shift operators. So n is how many times we're going to shift. If we shift 3 times, we're going to multiply by 8. If we shift right 3 times, we're going to divide by 8. So this works very nicely for multiplying by powers of 2. We can also use our bitwise shift operators to check the status of bits. So it's very common to shift things either to the most significant bit, or the least significant bit, and then use masks to check them.